Hello students, in previous lecture we have studied about the stacking of the spheres in the crystal structure which results in the formation of that is SCP or SCP type of layers in two-dimensional arrangement of those spheres, as well as results in the formation of that is simple cubic unit cell structure as well as cubic close packing structure in which FCC type of unit cell formation takes place while spheres are arranged in three dimensions. Then the coordination number. Then see here, first of all we have to discuss about the what is coordination number in close packed structure. Then see here, coordination number of close packed structure. See here, coordination number is known as, it is a total number of spheres which is directly attached or touches to the sphere, that is called as coordination number. And that coordination number of any crystal lattice in any arrangement of the crystal lattice, whether it is in one dimensional or two dimensional or it is in three-dimensional arrangement of those spheres in the crystal lattice. Then first of all, in simple cubic crystal structure, that is in three-dimensional structure of the crystal lattice, if it is of simple cubic crystal structure type, then coordination number is 6. Then here, out of that 6 spheres, 4 spheres are in same layer, and here one sphere is layer below to it and one sphere in the layer above to it. That means there are 6 spheres which are directly contact with that sphere. Then that is the coordination number of simple cubic crystal structure. Then one more type of crystal lattice are formed in three-dimensional arrangement of those spheres, that is in HCP, hexagonal closed packed structure, or it is CCP, that is cubic closed packed, that is in type of FCC, that is face centered cubic packed structure. Then in those type of crystal structure, coordination number is 12. Then see here that here coordination number is 12 means here 6 spheres are in the same layer and 3 spheres are from the layer above to it, and 3 spheres from layer below to it, like that. Coordination number in HCP type of or CCP type, that is face centered cubic crystal structure, that is of 12. Then see here that coordination number, which is the measure of the close packing of that spheres in the crystal lattice. That means here, if coordination number is more, then that compactness of packing of those sphere is greater. That means those are more efficient, and here compactness is greater. Compactness of arrangement of spheres is greater. That means spheres in HCP or CCP are most tightly packed than in SCC, that is simple cubic crystal structure. That means here the magnitude of the compactness, that is efficiency, packing efficiency is greater in HCP or CCP than the simple cubic crystal structure. Then here we have to discuss about few more concepts which is related with the packing efficiency of that crystal lattice or crystal structure, that is voids. All of you have studied about that. There are 2 different types of voids are formed while packing of those spheres in 2-dimensional as well as in 3-dimensional packing of those spheres in the crystal lattice. See here, if there are SCP, that means square close packed structure in 2-dimensional arrangement, in which there are that voids are of square type. In HCP, that is hexagonal closed packed, in 2-dimensional arrangement of the spheres in crystal lattice, then voids that are triangular in shape, which are alternately arranged, that such that the apex of those triangular voids get alternately arranged, that half of the apex of those triangular voids are takes place in upward direction, while of others are takes place in downward direction. And here voids are of triangular type, and here in SCP it is of voids are of square type. Then in 3-dimensional arrangement of the spheres, which results in the formation of simple cubic crystal structure in the 3-dimensional arrangement of that crystal lattice, and in simple cubic crystal structure it is of also square type. But here when those spheres, that is SCP layers when arranged in 3D pattern or 3D arrangement, then it results in the formation of CCP, that is cubic closed packing or packed structure, crystal structure, or that is of FCC type, that is face centered cubic crystal structure, in which voids which are formed are of two types, Then one of the void, that is tetrahedral voids, and another type, that is octahedral type of voids are formed in the three-dimensional arrangement of the spheres in CCP type or FCC type crystal structure. Then here tetrahedral voids are formed, which is that there are two tetrahedral voids are formed. Two tetrahedral voids are formed per atom, and here one octahedral void are formed per atom. That means here if there are n number of spheres are there, then there are 2n number of tetrahedral voids and n number of octahedral voids. That is about the different types of voids formed in the different type of crystal structures. Then those voids are also useful to explain the packing efficiency of that crystal lattice. Then we will discuss detail about packing efficiency in simple cubic unit cell as well as in BCC, that is body centered cubic unit cell, and face centered cubic unit cell. Then first of all we have to discuss on the packing efficiency in cubic unit cells, and all of you have studied about that. Cubic unit cells are of three types. First one, that is simple or primitive type of simple cubic unit cell, and we will discuss about the packing efficiency in simple cubic unit cell. Then see here, what is packing efficiency? Packing efficiency, it is a measure of how tightly particles are packed together in the arrangement of those crystal structures. Packing efficiency is nothing but it is a fraction. It is a fraction of total volume of spheres occupied, which is arranged in crystal lattice. That means here that packing efficiency is also calculated by, that is volume occupied by spheres in unit cell upon total volume of that unit cell into 100. Then we get the percentage of that packing efficiency cell in the crystal structure. Then let us study about the packing efficiency takes place in the simple cubic unit cell. Then first of all, see here the structure or the figure of three-dimensional arrangement of the spheres in the simple cubic unit cell. All of you have studied about that. In the simple cubic unit cell, there are total 8 particles which are present at each 8 corners, which are closely packed and touches to each other. See here, in the simple cubic unit cell, the front face, that is front face of that cubic unit cell, in which there are 4 particles which are closely packed. Then see here that vertex of that unit cell is labeled as A, that is B, C and D. That means the face of that cubic unit cell A, B, C, D, in which that corner, that's 4 spheres which are arranged at each corner of that simple cubic unit cell. Then all of you have observed that here P, Q, R and S, if here those points are labeled as it is. Then here AP is R. R means it is a radius of that sphere. Here also PD is also R, that is radius of sphere. Here QD is R, QC is also R, that is radius. Here RC and BR is R, that is radius of those spheres. Then let us consider AB, which is the edge length of that cubic unit is A. Then see here, let us consider A is edge length of simple cubic unit cell, and R is the radius of sphere. Sphere means particles. Those particles are, it may be atom, molecule or ion. Then see in the figure and you may write the relationship between A and R. That is, from figure you can observe it and you can write it like this, that is A is equals to 2R. Therefore we have to write R is equals to A upon 2. That is the relationship between A and R in simple cubic unit cell. Then see here, volume of unit cell. Volume of unit cell, all of you have studied about that. Volume of unit cell means volume of cube. That unit cell is of cubic type. Therefore here edge length is A. Therefore A into A, that means A cube. That is A cube is a volume of unit cell. Observe that cube, and all of you have learned about that. The volume of cube is length into length into length. that is here edge length is A, therefore A into A, that is A cube. As well as here volume of, we have to calculate the volume of sphere. Sphere means that particles, and as particles are in spherical shaped, therefore volume of sphere, all of you have studied in maths, that is it is 4/3 pi r cube. Then we can put in the value of r in this equation. See here r is equals to A/2. Therefore we have to put down the value of r in this equation. Therefore we get volume of spheres or particle, that is volume of one sphere, is 4/3 pi, here r means A/2 cube, bracket cube. Therefore simplifying we get 4/3 into pi into A cube upon 2 cube, that is 2 into 2 into 2. Therefore simplifying this we get here pi A cube upon here 4 get cancelled, and here we get, that is pi A cube upon 6, that is the volume of one sphere, one particle. Here we get the volume of one particle or sphere. But in SCC, in simple cubic unit cell, there is total number of atoms. Number of atoms is equals to 1. That means here n is equals to 1, that is number of atom is 1. Therefore here volume of one sphere is the volume of particle, and which is occupied in the cubic unit cell. Therefore here we can get the packing efficiency. Packing efficiency means it is a volume of spheres in unit cell. In unit cell, sphere upon total volume of unit cell. Therefore here volume of sphere in simple cubic unit cell, that is pi A cube upon 6 upon here total volume of unit cell. Volume of unit cell is A cube. Therefore here upon A cube. Here if we have to get percentage, then we have to multiply this by 100. Therefore here we can multiply this by 100, and therefore here we get, that is pi A cube upon 6 A cube into 100. Here A cube get cancelled, and we get pi, that is 100 pi upon that 6. Simplifying this we get the percentage of volume occupied by the spheres in simple cubic unit cell is 52.36%. That is percentage of volume occupied by spheres in SCC, that is it is a 52.36%. Therefore the empty space, that is percentage of void in SCC, that is 100 minus 52.36, that is here we get 47.64. 47.64, that is the percentage of void present in the SCC, and that is about the packing efficiency in simple cubic unit cell. Then we will discuss about packing efficiency in BCC type of unit cell. Then observe the figure, and all of you have studied about that. In BCC type there are total 8 spheres at each corner, 8 corner of the cubic unit cell, and 1 sphere is inside the unit cell. Then we have to calculate the packing efficiency in BCC. Then observe the figure in which there are 3 spheres which are arranged on the diagonal, that is that diagonal of that BCC type of unit cell. Then here we can label those vertices in that figure of cubic unit cell. That is, here there are different types of triangle are shown in the BCC type of unit cell, from which we have to focus on that triangle FED. Then see here, observe the figure, and here we can observe that in triangle FED. See here, in triangle FED, angle FED is of 90 degree. See here, angle E, that is angle FED, is of 90 degree. Therefore, triangle FED is right angle triangle. Using Pythagoras property, we can find out the relationship between edge length A and R is the radius of that sphere. Then see here, in this triangle FED, that is FD square. Here FD is a hypotenuse. FD square is equals to FE square plus ED square. Then see here, FE and ED, observe the figure, and see here, FE is the edge length as well as ED is also edge length of that cubic unit cell. Then here, as FE is equals to ED is equals to A, that are the edge length of that unit cell. Therefore, here we get FD square is equals to A square plus A square. Therefore, here FD square is equals to 2A square. Therefore, FD is equals to root 2A. Then, one more triangle you should observe here, that triangle AFD in the figure. See here, in triangle AFD, in which angle ADF is of 90 degree. Observe the figure in which angle ADF is of 90 degree. Therefore, triangle AFD is also of right angle triangle. Therefore, here using Pythagoras theorem, AF square is equals to AD square plus FD square. FD square. Observe the figure and you may find out that here AD square, AD is also edge length. That is, here AD is also edge length of that unit cell. And observe here FD, all of you have already calculated that value of FD. Then putting the value of AD, that is A square, plus FD, that is root 2A, and square of it, that is square. Therefore, here we get a square plus root 2a bracket square, that is 2a square. Therefore, here we get af square is equals to 3a square. Therefore, af is equals to root 3a. That means here we get fd is equals to root 2a and af is equals to root 3a. Then here observe the figure carefully and you may find out that af is here. af is 4r, because see here on af is a diagonal which joins the opposite vertices of the opposite faces of BCC unit cell. Then on that diagonal 3 spheres are arranged which touches to each other. Therefore, see here in the figure that we get AF is equals to 4R. Therefore, putting the value of 4R in this equation, therefore we get 4R is equals to root 3A. Therefore, here we get the value of R here. Therefore, R is equals to root 3A upon 4. Calculate the packing efficiency then using this formula. Therefore, first of all, we have to find out the volume of cubic unit cell. Cubic unit cell. Here in the BCC type of arrangement or BCC type of unit cell, that cubic unit cell, volume of unit cell, cubic unit cell, that is A cube. And we can calculate the volume of sphere, one sphere or one particle, that is 4 upon 3 pi r cube. Then putting the value of r in this equation, therefore we get 4 upon 3 pi r, that is root 3a upon 4, that is bracket cube, because r, the value of r is root 3a upon 4 and here r cube is there, therefore root 3a upon 4 bracket cube. Simplifying this, we get 4 upon 3 pi, see here, root 3 cube, that is root 3 into 3, that is 3 root 3 into a cube upon 4 into 4 into 4. Simplifying this, we get that 3 get cancelled as well as 4 get cancelled. Then here we get the value, that is root 3 pi a cube upon 4 into 4, that is 16. That is the volume of one sphere. And in BCC type of unit cell, there are total 2 number of atoms. 2 atoms are present or 2 particles are present. That is 1/8 the particles at each 8 corner. Total we get 1 atom and 1 total atom present inside the cubic unit cell. That is total 2 atoms are there. Therefore, here we get the total volume occupied by 2 spheres in BCC is equals to, see here, it is a volume of one sphere. Therefore, here we get the volume occupied by 2 spheres in BCC type of unit cell, that is root 3 pi a cube upon 16 into 2. Therefore, simplifying, we get, that is 2 ones are 2 8s are Therefore, here we get root 3 pi a cube upon 8. That is the volume, total volume of spheres in BCC type. Therefore, here we get the packing efficiency, that is according to the formula, volume of spheres in BCC upon total volume of unit cell into 100. Then here we get the percentage of volume occupied by spheres in BCC type. Therefore, here packing efficiency in BCC type, here we get root 3 pi a cube upon 8 upon a cube into 100 into 100. Therefore, here simplifying this, we get that root 3 pi a cube upon 8 a cube into 100. Here we get a cube get cancelled, and here we get that root 3 pi into 100 upon 8. Simplifying this, we get 68%, and therefore we get the percentage of void in BCC is 32%. That is about the packing efficiency of simple cubic unit cell as well as body centered cubic unit cell. Then here packing efficiency in FCC type, that is face centered cubic unit cell, is greater, that is about 74%, and void reduces in FCC than the BCC and SCC. That means here BCC is more efficient than simple cubic unit cell, and FCC is most efficient than the BCC and simple cubic unit cell. That is about the packing efficiency of the three types of, that is simple cubic unit cell, body centered cubic unit cell, and face centered cubic unit cell. There are few numerical problems which is based on those formulas of packing efficiency. You may solve those numerical examples from your textbook using those formulas. Thank you.